we can start with our discussion. So,
Hi, Marcus.
Hi, Anup.
Just was listening to
hi
your talk 2
everybody
seconds ago.
in the auditorium. We're now ready to talk and receive questions from the auditorium. Let me stimulate the beginning. It's always a general question from the auditorium. What's better, SiC or GaN? And it's in general something everybody of you can put his comment where GaN is better than SiC, or where to have a crossover area. So I want to let you start to comment on that, what I put into the stage. Stephan, you may have an idea.
Yeah, sure. So maybe I also include silicon. So I think that there will be space for all of them actually, right? And there will be no single material platform or device platform left in the future. So I think silicon carbide particular has some advantages towards higher voltage classes, so beyond 1.2 and beyond. I think there gallium nitride will be tough for gallium nitride to compete with silicon carbide, but yeah, below several hundreds of volts, I think GaN is a very good alternative, especially if I see the advances, for example, of EPFL for the GaN on silicon devices, where they achieve very nice devices. So, but still, from what I've seen, the packaging or the module point of view for GaN is still a bit of a challenge, where SiC is ahead. So I think all these three technologies, they will have their niche. And yeah, maybe silicon will go down a bit, but GaN and SiC will go up. But none of them, I think, will disappear.
Thank you, Stephan. There is a question addressed to Anup. Was the efficiency shown based on calculation or measurement?
They're based on a calculation done using the measured switching losses and conduction losses over temperature for the devices. So it is a calculation, but it's based on the measured value of the losses.
Okay, Anup. And the next question is all, so to you, does the efficiency and totem pole PFC includes also fan EMI filter losses?
It does not. And that I made that clear on the slide there. It does not. It's just the losses in the power devices alone.
Okay. The next addressed to Hitachi and ABB. It was presented that high K devices exhibit lower current overshoot. Is this having any impact on the short circuit capability?
So the improved interface quality, there are papers that show that the improved interface quality, or let's say another improved interface quality, shows some impact on the short circuit. For our particular devices, we didn't perform specific tests yet, but typically also if you start at lower VGS values in the short circuit event, you get a larger overshoot in the short circuit actually. Yeah, this is what you see in short circuit if you have a bad interface. For our devices, where we are quite a better interface, we should not see this overshoot, but we have to do these measurements. So this would be the effect of a high K in a short circuit event. or of this drain current overshoot.
The question to Anup. UnitedSiC has long been a proponent of SiC JFETs. Why has United Silicon departed from JFETs for Gen 4?
I think I misunderstood the question, but the devices, the Gen 4 devices are still using the cascode configuration that we are known for. And it is built on top of a normally on very low resistance silicon carbide JFET technology. And inside the package, we put a low voltage MOSFET in series with the JFET to turn it into a normally off switch. It's the same configuration.
Thank you, Anup. That's what I had understood from the presentations and the material. That's still the JFETs in cascode. The next question is addressed to StarPower. If you had the possibility to change a parameter on the SiC substrate to improve power cycling behavior, what physical parameter would you modify?
I think this is a tough one. I mean, it's known that from IGBTs, there have been differences in different chip generations, like what's the English word for it? The amount of how the current flows and how the current is distributed over the surface of the chip. So yes, those differences are probably existent in different SiC generations too. I think what I tried to make clear in the presentation was that so far we have, let's say, not tested too many, let's say, like the new chip generation yet. So we're kind of guessing if there are differences, if the chip has, let's say, the chip design has something to do with it, with the capability, or if it's more the size of the chip. And let's say our suspicions are more that the main difference in power cycling comes as SiC chips are, let's say, significantly smaller. So the number of bond foots is also reduced. And if you have fewer bonds, then you get fewer currents over the same area. And then, of course, the bond liftoff will come significantly quicker. So I think, let's say, that's something we need to look at when we do more tests, really.
Yeah, to me, what I remember from my time, lower temperature in cycling is based on bigger die size, and that has an impact on lifetime. So that's something that has to go back to the physical design, where people look into it, where they design it for a certain lifetime and certain conditions.
Yes, and
okay, Markus. The next one is again to Anup. How high are the losses on the snubber in the totem pole PFC conditions?
Good question. So in our data sheet, and our user guides, we show you what the snubber losses are by directly measuring them across the snubber resistor. So they're on the order of a few microjoules per switching cycle. So you multiply that by the 100 kilohertz switching frequency, and it turns out that you can just use surface mount components for the snubber. I mean, I don't remember the watts off the top of my head, but we use just surface mount snubber components. Most of the actual loss from the snubber capacitor is dumped in the transistor during turn on, not the resistor. And what the snubber is doing for us, is allowing us to use a very low RG and still keep very good looking waveforms. So you can get the best efficiency benefit from this device.
The next question is again to you, Anup. Do you plan to release less inductive 7-lead packages for your fourth generation SiC MOSFETs?
Yes, absolutely. There's a whole range of other derivative parts that will start coming out next year. The DFN 8x8 style package, the D2PAC 7 lead style package, and so on. Yes.
Okay, the next question is to StarPower. Looking at the number of achieved cycles looks to be factor 2 lower than for the IGBT, your first slide. Was it the same package materials, or is that due to the different CTE of SiC?
Okay. So first answer, no, it's not the same package, but yes, the number of cycles is significantly lower what we observed compared with IGBTs. And what we, let's say, it's too early to say specifically, you know, it's for this and that reason. That was kind of the whole point. You need more tests for that. But as I just tried to indicate, what we think is the main factor here is the number, let's say the top connections, the top side connection of the chip. You know, if you look at the power cycles where we keep the current constant, then you see, you know, no temperature runoff on the thermal resistance. And if we open the packages, it's basically just, you know, a whole array of bond wires, basically, which you can push aside. So we think if we can improve the top bond connection, then the number of cycles can be raised significantly. And there's obviously a number of ways that can be done. One thing would be copper solutions, you know, either, let's say, copper bonds, or like a copper plate to have a small copper plate on top of the chip to have a better current distribution, and then per bond copper on top of that. That's of course as a sinter solution for reliability reasons as well. But you know, this is all something which is deviating quite a lot from standard module technology. So we're kind of in R&D area here, and we need more tests. Another thing, of course, would be larger chips. So the chips we used for those tests are comparatively small. If you compare the same current per chip with an IGBT, they're less than half of the size. So of course, a smaller chip size on the same current means more current has to go over the same number of bond, or smaller number of bond feet or bond wires. And that's why we think the number of power cycles is smaller.
Thank you, Markus. The next question is again to Anup. In the snubber, if the energy is dissipated in the transistor, would that make the transistor hotter and thus less efficient? Compared, that will be the case that the energy is dissipated outside of the resistor.
Good question. So the first thing you have to realize is the value of the snubbers we are talking about is extremely small. And what we are doing with the snubber is comparing, for a practical design, you have to slow the waveforms to a point where it's reasonable, overshoots are reasonable, EMI is reasonable. So you have a choice. Either you use a gate resistor and slow it down, or you use the snubber technique we described. And what you will see is that the snubber technique allows you to use a smaller gate resistor and actually come away with much lower EON plus EOF total losses. So in reality, what ends up happening is, even though some of the snubber capacitance energy is dumped in the transistor at turn on, in effect, the EON plus EOF is lower in this situation, and the transistors actually run cooler. It's a better overall solution. There's a lot of information on our website that explains how all this works.
Thank you, Anup. The next question is again to Marcos. Power cycling on SiC devices may look worse than IGBTs. However, in practice, SiC MOSFETs will run cooler and delta T tends to be lower. IGBT will run warmer and have a worse delta T. Do you have the same conclusion?
Yeah, I think you have to keep, let's say, several issues about it here. I mean, yes, the number of cycles required really depends on the application. That's something, I think this is not chip technology specific. Some, like automotive, for instance, they have a high cycle requirement due to the drive cycles of the car. If you have other applications, they're not really critical on power cycles. So, and also on the delta T. So if your delta T usually comes if you want to get the maximum power out of the package. And again, for applications where this is specific, then yes, it will become an issue. And with I think the real important thing is how you get the power, the heat out of the package as well. Technically, the chip temperature, the chips will get hot for silicon carbide as well because they're smaller. It's more power on a small area. But if you can cool it properly, if let's say your thermal resistance within the module is low and you have a good outside cooling, then that's technically not a big issue. So, yeah.
Okay, thank you. The next question is again to Anup. It's specific to the cascode, and the question is that the low voltage MOSFET can be driven into an avalanche operation. That's the question.
It's a good question. And it certainly can be driven into avalanche, which is why the MOSFET that we use is not one that you can buy off the shelf. It is actually a MOSFET with an integrated TVS-like avalanche clamp diode inside every cell. And it's qualified in a special way by biasing the device into avalanche for the full 1,000 hours of burn-in.
Thank you, Anup. So the next questions are coming in. Gen 4 UnitedSiC devices, are they very different from the use to the Gen 3 devices?
I see. It's a good question. So if you're already using Gen 3 devices, can you use the Gen 4 devices in the same circuit and drive them the same way? Yes, largely you can. You have to pay attention to the fact that all the devices are roughly half in size. So you need to pay attention to what the datasheet is saying about the thermals and what kind of snubber or other recommendations we have. Same gate drive voltages, etc., can be used.
That's a question I want to address to Max. What are the most attractive applications for SiC adoption in industrial areas by market size?
Yes, so definitely in the industrial area, there is different kinds of applications. There's DC to DC conversion, where we see growing use of silicon carbide products, for example, in battery energy storage systems. That would be one example. And also in charging, there we see a growing demand. So this is definitely one of the, I would say, the largest growing markets for silicon carbide application that we currently see. as of right now, I mean, the most of the industrial area is still using IGBT technology. So the major turnover is still generated with the silicon products, but we do see a strong increase in the adoption of silicon carbide.
Thank you, Max. Again, Anup. Are Gen 4 devices recommended for new designs, or are there applications where Gen 3 is better?
Where Gen 3 is better. Well, for the same RDS on, the Gen 3 has a bigger die size, and there may be some cases where that becomes an important consideration. So Gen 3 would be a better thing to use. But generally, all the switching losses and other factors are just better with Gen 4. So in the vast majority of applications, you'll end up finding if you're doing high frequency switching and power conversion, or if you need better short circuit handling in a motor control type application, the Gen 4 devices are more advanced for that. But the Gen 3 devices are very good and they work perfectly well for most applications. The big thing about Gen 4 at this point is it's 750 volt, not 650 volt. So if you have the need to work off of a 500 volt rail, we don't have a Gen 3 option for that. So you need the Gen 4.
Thank you, Anup. At the moment, we have no more open questions. I can just summarize that we have very exciting moves in the wide bandgap area, and that the devices have covered now a broad range of applications in industry areas. Now the next question to Anup come in. What's the main market focus for the Gen 4?
So I think there was a slide in which I showed our 4 main market segments that we focus on. The parts were, during this long COVID season, we spent the time AEC qualifying these first parts because its main market focus in the automotive space is in onboard chargers and DC-DC converters, because they work well in totem pole PFC, they work well in LLC. Then these same devices with the right package types are going to be used in servers and telecom rectifiers, same kinds of circuits. In the solar space, both in inverters, in choppers, and in energy storage units. That's another area. And there's another area that that looks interesting with these devices, because we have some super low resistance ones coming out, which is solid state breakers. I think I covered them all. Yeah.
Thank you, Anup. So with a couple of minutes left, any questions and comments between the presenters? How you feel about an event that's virtually and that not run real as a conference? I may like to hear you.
Can't wait for this to be over so we can have a conference where we can actually meet people. We've been working from the home office way too long.
Oh yeah, oh yeah. But on the one side,
the
it's
end
safe.
is in sight.
Yeah, safety at the moment is one of the highest. Yes. So I see a Danfoss question. Do you see adoption of 1.7 kilovolt in industrial applications? What would be the specific applications?
Yes, so Let me take that question. There's definitely applications where 1.7 kV devices are being used and are being requested. So in the industrial size, of course, it depends on the module layout. But as I explained in my presentation, Danfoss Silicon Power provides a customized module layout, so we can adapt to the link voltage and to the creepage and clearance requirements of the application. Regarding the specific applications, I must redirect you to our sales department, but I definitely know there are certain applications and projects that are custom-oriented projects that use the 1.7 kV. Thank you.
Thank you, Max. Anup, again, will be United Silicon Carbide producing larger, normally on JFETs for solid-state breakers?
Yeah, and so if you're interested in normally on JFETs for solid-state breakers, there's only a small number of them on our website, but it's better you reach out to us directly because we do have very, very low resistance chips normally on JFETs that are specifically made for this application. There's one that's down near 5 milliohm 1200 volt. One chip.
Thank you, Anup. The next question again to you, Anup. You said your SiC FET will be cost competitive to SJ MOSFETs. At which time horizon do you see cost parity?
So we are doing it now. I think if you if you look at the not so informative online distributor pricing stuff, you'll see it there. And also, where we serve mainstream applications in Asia for everything below 60 milliohm, 40 milliohm, 20 milliohm, all those classes, we compete effectively. And below that, there's no devices in silicon. You can only get silicon carbide below 10 milliohm.
Thank you, Anup. So we come closer to an end. The final 2 to 3 minutes are running. And at the moment, we have no additional questions on screen. But there is the next one. Again to Anup. Are you going to release SiC MOSFET devices with higher voltage ratings in the short term?
So the first answer is we don't make silicon carbide MOSFETs. We make a cascaded configuration of the high voltage JFET, that normally off transistor. And yes, there's a roadmap for this generation 4 version to have higher voltage types. Currently, we have in Gen 3, 650 volt, 1200 volt, and 1700 volt. I think in Gen 4, it'll go a little bit higher in voltage.
Thank you, Anup. We are at the end of this question and answer session. Thank you, gentlemen. Have a nice evening or lunchtime soon. Wherever you are sitting, enjoy the day.
Okay, thank you very much.
Thank you, Bodo.
Thank
Thanks
you.
for
Thank you very
organizing
much,
it.
Bodo.
Everybody.
Thank
Nice
you.
seeing you all.
Thank you. Bye.
Thank you.
Bye.
Thank you for
Bye.
organizing.
Bye.
Stay healthy. Bye-bye.